Right now, billions of tiny somethings are entering your eyes every second. They came from the screen across the room, or from the lamp on your ceiling, or from a star 26 trillion miles away whose light has been travelling toward you for the entirety of your life. We call them photons, and almost everyone has been shown a picture of one, a small bullet of light, a tiny ball moving in a straight line. Tonight I want to tell you that picture is wrong. A photon, as physics actually describes it, may be the size of an atom or the size of the universe. It may have no mass at all, or a mass so small no instrument on Earth has been able to find it. When it lands on a detector, the universe picks the specific spot it deposits its energy, and we do not yet know how. So if every act of seeing is built on a particle physics cannot fully describe, what does that say about the world we think we are looking at? Settle in. Subscribe if you have not, and stay with us tonight, because the journey we are about to take leads to a horizon most of physics never quite reaches. Let's begin. Part 1. The Friendly Picture. Right now, as you're sitting wherever you're sitting, an extraordinary thing is happening that you almost never notice. Billions upon billions of tiny somethings are entering your eyes every second. They came from the lamp across the room, or from the screen you might be looking at, or from the night sky if you're outdoors, and they have been travelling at the fastest speed anything in this universe is allowed to travel. They strike the back of your eye, slip into the molecules of the rods and cones in your retina, and disappear. In the process, they leave behind a small jolt of energy. Your brain reads that jolt as light. It is how you see. It is happening continuously, in numbers your imagination cannot really hold, and you have never once felt a single one of them arrive. We call these somethings photons. The word means particles of light, and almost everyone, at some point, has been shown a picture of one. The picture usually looks like a little bullet of light, or a tiny ball, or sometimes a curly squiggle drawn next to a wavy line, with an arrow on the end to show it is moving. It looks small, it looks confined. It looks like the kind of thing that, if you could shrink yourself down small enough, you could hold in the palm of your hand. I want to tell you tonight that this picture is wrong. Not slightly wrong, not a useful simplification. Wrong in the deep way that matters. A photon, as physics actually describes it, is one of the strangest objects in the universe. It may be the size of an atom or the size of a galaxy. It may have no mass at all, or it may have a tiny one that no experiment on Earth has been able to find. It may be a wave, it may be a particle, it may be something that pretends to be either depending on how you look at it. And when you measure where one of them actually is, the answer the universe gives you is, in a deep and unsettling sense, random. Tonight we are going to take a long, slow look at the photon. Not the cartoon. The real thing, as physicists understand it after 100 years of careful experiments, and even more careful arguments about what those experiments mean. We're going to begin with the friendly picture you already have, the small ball of light moving in a straight line at the speed every physics teacher has told you about, and then we're going to take that picture apart layer by layer until you are left with the much stranger, much more beautiful thing that is actually travelling through your eyes right now. I should warn you that the destination of this journey is not a tidy answer. There is no moment in any part of what is to come where the lights come up and a presenter walks out and tells you what the photon really is, in plain language, once and for all. There is no such moment because physics does not have one yet. We are going to walk you to the edge of what is known, and then a few small steps past it, and then we're going to stop there together and look down. But before we can appreciate the depth of how strange it is, we have to know what we think we know. So let me start with the friendly picture, the bullet of light. The friendly picture goes like this. Light is made of photons. Photons are small. They travel in straight lines, in vacuum, at exactly 299,792,458 meters per second. We measured this speed with extraordinary precision in the 20th century, and in the year 1983 we did something curious. We turned it around. Instead of measuring how fast light goes in meters per second, we redefined the meter in terms of how far light travels in a fixed fraction of a second. The speed of light, in other words, is no longer something we measure. It is something we have built into the rulers we use to measure everything else. When two photons travel side by side, they do not interact directly. They pass right through each other. When a photon hits an electron, it can transfer some or all of its energy and disappear, or it can scatter off and continue at a different angle. When a photon strikes a leaf, some of its energy can be captured to drive photosynthesis. When a photon strikes the back of your retina, its energy can trigger a single molecular conformation change in a pigment called rhodopsin, which sets off a cascade of electrical signals that your brain learns to recognize as light. In the friendly picture, all of this is happening to a small thing, a discrete unit, a bullet. The bullet has a color, which is to say, a wavelength, and a corresponding energy. A red photon carries less energy than a blue photon. A blue photon carries less than an ultraviolet. A gamma-ray photon carries enormous energy. A radio photon carries almost nothing, but each one is, in the friendly picture, a small thing that can be counted. Photons are everywhere. The cosmic microwave background, the leftover heat of the Big Bang, fills the universe with about 411 photons in every cubic centimetre. A sunny day at the equator delivers something on the order of 4 times 10 to the 21st photons per second per square metre to the surface of the Earth. When you look at a single match flame across a dark valley at night, your dark-adapted eye is detecting flashes at the threshold of about 5 to 14 photons absorbed by the rods in your retina. Single photons. You can, under the right conditions, detect single photons consciously with your own eye with no instrument at all. This was demonstrated in 1942 by Hecht, Schleyer and Pirenne, and confirmed at the conscious level in 2016 by Tinsley and her colleagues in a paper in Nature Communications. The dark-adapted human eye is a single photon detector. You are walking around with one of the most sensitive light measurement instruments in the natural world built into your skull. So the friendly picture is not a bad picture for everyday purposes. It captures something true. Photons are countable. They have energy. They travel at the speed of light. They can be detected one at a time. The picture is friendly because it is intuitive, because it lets you imagine light as something concrete, something almost tangible. The trouble is that it is wrong in nearly every detail that matters once you start asking how it works, because here is the question that starts the whole story unraveling. If a photon is a small thing, a little bullet of light, then what determines its size? How big is it? When 2 photons pass each other, what is the size of the region where one of them is and the other is not? When a photon enters your eye, how large was it just before it arrived? Was it the size of an atom? The size of the lens of your eye? The size of the room? Was it the size of the sun having begun its life at the surface of a star 93 million miles away, travelling for 8 minutes, and then ending when it hit the back of your retina? Most physics teachers do not answer this question. Most physics teachers, when they are honest, hesitate. Because the friendly picture does not have a good answer. It treats a photon as a small particle, but it does not say what determines the size. It just waves a hand, and the moment you press on it, the friendly picture starts to crack. So tonight we are going to walk into the crack. We are going to look at the experiments that first showed that the friendly picture had to be wrong. We are going to look at the question of whether photons even have mass. Because the answer to that question, you are going to discover, is not yes and not no, but something far more uncomfortable. We do not know. We are going to look at what a single photon actually looks like mathematically when physics is being honest. And we're going to look at the moment when a photon spread across the entire detector picks one specific spot to land. And we're going to find that there is no known reason it picks that spot rather than any other. The universe just picks, every single time. By the end of this journey, the word photon is going to look enormous to you. It is going to be a word that names a thing physics does not actually understand, even though physics can predict everything that thing does to a precision that is almost beyond comprehension. And what I want you to feel by the end is not confusion, but something closer to awe. Because the cartoon was small, the real thing is vast, and it is sitting right now on the back of your eye, having travelled here from a distant star or from the screen across the room, carrying with it a mystery the cleverest minds in the history of science have not been able to solve. So get comfortable, settle in, and let me show you what we have spent 100 years discovering about the smallest thing in physics, the little bullet of light, which is not a bullet, and may not be little, and may not even be properly called a particle. Let me show you the photon. Part 2. The photoelectric crack. The story of how physicists came to abandon the friendly picture begins, like a surprising number of breakthroughs in physics, with somebody noticing something they were not looking for. The somebody, in this case, was Heinrich Hertz, a German physicist working in 1887. Hertz was working on a setup designed to confirm something James Clerk Maxwell had predicted 20 years earlier. Maxwell had written down a set of equations that described electricity and magnetism as two aspects of a single underlying field, and his equations made a startling prediction. If you wiggled an electric charge back and forth fast enough, a wave should travel outward from it at the speed of light. The wave would carry both an electric and a magnetic disturbance, perpendicular to each other and perpendicular to the direction of travel, and it would obey all the same rules that light obeys. Maxwell's equation said that light was a wave in the electromagnetic field. Hertz set out to test this by generating waves at much lower frequencies than visible light and showing that they had all the right properties. He had two pieces of apparatus. The first was a transmitter, which used a spark gap to generate brief bursts of electromagnetic radiation. The second was a receiver, a separate loop of wire with its own spark gap positioned across the room. When the transmitter sparked, the radiation crossed the room and induced a tiny spark in the receiver. Hertz could measure the relationship between the two sparks and confirm that the radiation behaved as Maxwell had predicted. The inconvenience was this. Hertz noticed that if he enclosed the receiver in a dark box so he could see the spark better, the spark got even harder to detect. If he opened the box and let light fall on the receiver, the spark was easier to produce. Light, somehow, was making it easier for the receiver to spark. This was strange. Light hitting a piece of metal should not, in any obvious way, affect the metal's ability to produce sparks. The mainstream theory said that light was just an oscillating electromagnetic field, and the strength of that field was determined by the intensity. If you wanted more effect, you wanted brighter light. But that was not quite what Hertz was seeing. Other physicists picked up the thread. Through the 1890s, careful experiments established that when ultraviolet light fell on a freshly cleaned piece of metal, the metal acquired a positive charge. Something was being knocked loose. Nobody yet knew what. In 1902, a Hungarian-born physicist named Philipp Lenard, working in Germany, finally pinned the effect down. He set up a careful experiment in which ultraviolet light shone onto a clean metal surface inside a vacuum tube. The light, he confirmed, was kicking electrons out of the metal. He could measure the kinetic energy of those electrons by setting up an opposing electric field that slowed them down and stopped them, and then reading off the voltage at which they were just barely stopped. And here Leonard noticed something that nobody could explain. The kinetic energy of the kicked-out electrons did not depend on the brightness of the light. If you turned up the brightness, more electrons came out, but each one came out with the same energy as before. The brightness controlled the number. It did not control the speed. The energy of each electron instead depended on the colour of the light. Light with a higher frequency, light from the blue and violet and ultraviolet end of the spectrum kicked out faster electrons. Light with a lower frequency, light from the red end, kicked out slower electrons, until you went below a certain threshold frequency, and then the light kicked out no electrons at all, no matter how bright you made it. This was, in the most polite way you can put it, a problem. The wave picture of light made a very clear prediction. The energy in a light wave depended on the amplitude, the brightness. Brighter light carried more energy. The frequency was just a kind of timing. The energy was in the amplitude, so if you wanted to give an electron in the metal enough energy to escape, all you had to do was wait. Turn up the brightness. Let enough energy pour in. Eventually, even dim red light given enough time ought to accumulate enough energy at the location of any given electron to kick it out. But that was not what was happening. Brighter red light, no matter how bright, did not kick out a single electron. Faint violet light, even at a brightness so low that classical theory said it would take hours or days for enough energy to accumulate at any one spot, kicked out electrons immediately. As soon as the light was turned on, with no delay at all. The brightness controlled how many electrons came out. The frequency controlled whether any came out at all, and how fast they were going when they did. This was completely incomprehensible in the wave picture of light. For a few years after Leonard's careful experiment, physicists tried to find ways to fix the wave picture. None of the attempts worked. The numbers just did not come out right. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, working on physics in his spare time after his day job stamping patent applications, wrote down an explanation that worked. The young man's name was Albert Einstein. The paper, published in the journal Annalen der Physik, was one of 4 extraordinary papers Einstein published that year. The papers are collectively known to physics historians as Einstein's miracle year. The photoelectric paper was the one for which, 16 years later, Einstein was given the Nobel Prize. Not relativity, the photoelectric effect. Einstein's explanation was as bold as it was simple. Stop thinking about light as a wave, he said. Or rather, do not stop entirely. Add to the wave picture a new idea. Light is also delivered in discrete packets of energy, and the energy of each packet is determined entirely by the frequency. Higher frequency, bigger packet. Lower frequency, smaller packet. The energy of a packet is E equals h times f, where f is the frequency of the light, and h is a tiny number that had been introduced 5 years earlier by Max Planck in an entirely different context, to fix a different problem about how hot objects radiate heat. The number h was so small that for any everyday light source, the number of packets being emitted per second was astronomical, which is why nobody had noticed that light came in packets before. You only saw the granular structure when you turned the intensity down so far that the individual packets started to matter. In Einstein's picture, the photoelectric effect made perfect sense. When light fell on a metal, each electron in the metal could absorb at most 1 packet of light at a time. If the packet carried enough energy to free the electron from the metal, to overcome what physicists later called the work function of the metal, the electron came out, with whatever leftover energy the packet had had above the work function showing up as kinetic energy. If the packet did not carry enough energy, no amount of patience would help. The electron could not absorb 2 packets simultaneously. Each interaction was 1 packet, 1 electron, all or nothing. Brighter light meant more packets per second, so more electrons could be freed per second. But each electron's energy was determined by the single packet it had absorbed, which was set by the frequency. This was the explanation. Simple, beautiful, every number came out right, and it was wildly controversial because it required physicists to take seriously the idea that light, which 50 years of experiments had established was a wave, was also a thing that came in particles. The light packets did not yet have a name. The name photon would not come along until 1926, when an American chemist named Gilbert Lewis coined it. But the idea was on the table now. Most physicists did not like it. The biggest opponent was Robert Millikan, an American experimental physicist at the University of Chicago, who simply did not believe Einstein could be right. Between 1912 and 1916, Millikan undertook one of the most painstaking experimental campaigns in the history of physics, specifically to disprove the photon idea. He found, instead, that Einstein was exactly right. E equals h times f. To the precision of his measurements, the relationship held perfectly. Millikan published his results in 1916, declaring that the predictions of Einstein's photon theory had been verified, even though, he wrote, the physical theory upon which they were based seemed to him to be untenable. He had set out to disprove Einstein, and he had ended up making the strongest experimental case for Einstein's theory that anyone had yet produced. He was given the Nobel Prize in Physics in 1923, and he never quite stopped grumbling about it. So by the middle of the 1920s, here is where physics stood on the question of what light is. Light, as Maxwell had shown, was a wave in the electromagnetic field. This was solid. Interference, diffraction, polarization, the entire structure of optics, all of them said wave. But also, as Einstein had shown and Millikan had reluctantly confirmed, light came in discrete packets of energy whose size depended on frequency. This too was solid. The photoelectric effect said particle. Both pictures had experimental backing. Both contradicted each other in their most basic claim, and nobody yet had any idea how to put them together. This is the crack the friendly picture opened. 30 years of careful work that took light from being a wave you could understand intuitively to being something that, when you looked at it carefully enough, refused to be just one kind of thing at all, and the strangeness was only beginning. Part 3. The chunk. Let me stay with Einstein's idea for a moment, because it is more revolutionary than it first appears. When you hear the phrase "a packet of energy," your mind probably reaches for some intuitive picture. Maybe a small wrapped parcel, maybe a discrete drop falling out of a wave, something that occupies a specific size and a specific place. But Einstein's claim was much stranger than any of those pictures. He was not saying that light consists of small countable objects, in the same sense that a bag of marbles consists of small countable objects. He was saying something more abstract. When light interacts with matter, the energy is delivered in chunks, and the size of each chunk is determined by the frequency of the light. The chunks are not little spheres flying through space. They are units of transaction. They are the minimum amount of energy that light can hand over in any single interaction. This is a subtle point, and it matters, because it explains why the photoelectric effect looks so strange the first time you encounter it. The chunks do not look like things, in the everyday sense of the word things. They look like rules about how energy is transferred between light and matter. But the rules are extraordinarily strict, and the rules have consequences that, the deeper you look at them, make less and less sense in any classical picture of how the world is supposed to work. Let me walk you through what those rules actually require. Imagine a small lamp that is producing light of a single colour. Let us say it is producing green light at a wavelength of about 530 nanometers. The energy of each green photon, in Einstein's picture, is about 2.3 electron volts. Now imagine that the lamp is producing this light very dimly, so dimly that on average only 1 photon's worth of energy is emitted every second. We can do this in the lab. Place a calibrated attenuator in front of a laser, and you can dial the output down until the photons are coming out one at a time with measurable gaps between them. Now place that lamp inside a darkened room, and across the room, set up an array of small detectors. Imagine a grid of 1,000 tiny pixels, each one a single photon avalanche diode capable of registering the arrival of 1 photon's worth of energy and turning it into a click. The grid is large enough that the dim green light from the lamp falls across all 1,000 pixels approximately equally. There is no preferred spot in the room. What does the friendly picture predict you will see? If light were a wave in the classical sense and 1 photon's worth of energy were arriving every second, that energy would be spread out across all 1,000 pixels equally. Each pixel would receive 1/1000th of a photon's worth of energy per second. After 1,000 seconds, each pixel would have received 1 full photon's worth of energy. But the pixels cannot store and accumulate it. The pixels are quantum mechanical devices, exactly like the calcium surface in the photoelectric effect, and they obey the same rule. They can absorb energy only in whole, photon-sized chunks. If less than 1 chunk's worth of energy arrives, nothing happens. So what actually happens in Einstein's picture? What happens is that, on average once per second, exactly 1 of the 1,000 pixels lights up. Just 1. The other 999 pixels remain dark. Which pixel lights up appears to be random, with each pixel having an equal probability of being the one. Over many thousands of seconds, the lit pixels are distributed evenly across the grid. But on any given second, only 1 pixel takes the energy. The others get nothing. Stop and feel the strangeness of this for a moment. A wave of light is spread across the entire detector grid. By any classical measure, the energy of that wave is distributed across all the pixels, and yet when the moment comes for the energy to be delivered, exactly 1 pixel gets it. All of it. The entire chunk. And nothing in classical physics predicts which pixel will be chosen. Nothing in the wave equation selects 1 pixel out of the 1,000. The wave covers them all equally, and yet, somehow, one of them fires, and the others do not. This is the rule Einstein wrote down. Energy is exchanged between light and matter in discrete chunks, and only 1 chunk can be exchanged at a time, and the location of the exchange is, as far as anyone can predict, random. Now, you might object at this point. You might say, surely the energy that hits the chosen pixel did not come from the entire wave. Surely it came from just the part of the wave that was actually located near that pixel. Maybe the photon, before it hit, was already small and concentrated in that region. This is exactly the objection that physicists in the 1920s tried to use to rescue the friendly picture. And it does not work. Because if you set up the experiment carefully, you can verify that the wave really is spread across the entire grid before the click happens. You can do double slit experiments where the wave clearly passes through both slits, Even when the photon is detected as a single click on one pixel behind the slits, the wave is real, the spread is real, and yet the click is always on one pixel. The chunk is not a small object hidden inside a wave. The chunk is the rule for how the wave hands over its energy, and the rule is so strict and so deeply built into the fabric of how matter interacts with light that it cannot be derived from any classical picture. It has to be inserted as a new and irreducible feature of how the universe works. This is why Einstein's 1905 paper was so radical. He was not just proposing a clever fix for the photoelectric effect. He was proposing that energy itself, when it is being transferred between light and matter, is not a continuous quantity. It is granular. It comes in indivisible units, and the granularity is not something we add as an approximation. It is fundamental. So by 1916, the chunk was real. The quantum was real. Light, somehow, came in indivisible packets whose energy depended on frequency. But the question of what those packets actually were, physically, remained completely open. Then, in 1923, an American physicist named Arthur Compton at Washington University in St. Louis did an experiment that made it almost impossible to pretend the photon was just a piece of bookkeeping. Compton was studying what happened when high-frequency X-rays scattered off the electrons in a target. The classical wave picture predicted that the scattered X-rays should have the same wavelength as the incident X-rays. The wave should hit the electron, set it oscillating, and the oscillating electron should radiate at the same frequency. But Compton found that the scattered X-rays had a slightly longer wavelength than the incident X-rays. The wavelength shift depended on the scattering angle, in exactly the way you would predict if you treated the X-rays as particles colliding with the electrons like billiard balls, transferring some of their momentum to the electrons and recoiling with reduced energy. Compton wrote down the prediction using a simple particle collision model with photons carrying momentum equal to their energy divided by the speed of light, and his formula matched his measurements precisely. The photon, in Compton's experiment, behaved like a particle in every detectable way. It had momentum, it collided, it bounced off. If you set up the experiment so you measured only the scattered X-rays and only the recoiling electrons, you saw what looked like two particles colliding. The wave picture could not explain it. The particle picture worked perfectly. This was the moment when physicists really started to take the photon seriously as a thing, rather than as a calculational device. Compton won the Nobel Prize for the work in 1927. But the photon could also still be diffracted. The same X-rays Compton was scattering could, in other experiments, be passed through crystal lattices and produce diffraction patterns that only a wave can produce. The same light that was kicking electrons out of metals was, in the double-slit experiment, producing interference fringes that only a wave can produce. Both pictures somehow were right. The photon was a particle. The photon was a wave. The photon was a chunk of energy delivered to one electron at a time. The photon was an extended wave that could pass through two slits at once. The photon was small. The photon was big. Depending on how you measured it, you got one answer or the other. Never both at the same time. Never neither. This was the situation in the late 1920s, when quantum mechanics as a coherent mathematical theory was just being born. The photon was the most baffling object in physics. The photon was also the gateway to everything that was about to come, because the same wave-particle duality that physicists had been forced to accept for light was about to be discovered in 1927 for electrons, and in 1928 for protons, and eventually in principle for everything. The chunk, the rule that energy is delivered in discrete units whose size depends on frequency, turned out to be the rule for all matter, not just for light. The photon was the first quantum object physicists had been forced to take seriously. It would not be the last, but the photon has remained, even now, the strangest of all of them. For every other particle in the standard model, we can write down a position. We can say where the electron is. We can build a wave function that describes where it is likely to be found. And we can measure that location to a precision limited only by our instruments. For the photon, even this much is not really true. The photon does not have a well-defined position the way an electron does. There is no clean answer to the question, what is the size of a photon? And as we are about to see, the closer you look at the wave side of the photon's nature, the larger the photon turns out to be. So we have crossed the first threshold. light is delivered in chunks. The chunks have a discrete size set by frequency. Each chunk goes to exactly one electron, exactly one detector pixel, even when the wave that carried the chunk was spread across an entire grid. This is the rule Einstein wrote down in 1905, the rule Millikan confirmed in 1916, the rule Compton extended in 1923. But it's only the first step into the strangeness, because now we need to ask what a single photon actually looks like, mathematically, when physics describes it honestly. And to do that, we need to look at the experiment in which a single photon travelling alone somehow interferes with itself. Part 4. One photon, two slits. There is a particular experiment in physics that has, more than any other, come to symbolise the strangeness of the quantum world. It is called the double-slit experiment, and you have almost certainly heard of it. You have probably seen a diagram, with a wall on the left containing two narrow vertical openings, and a screen on the right showing a striped pattern of bright and dark bands. The picture is iconic, but the version that matters most for our story tonight is not the simple version with bright light. It is the version where you turn the light down so far that there is, on average, less than one photon in the apparatus at any moment. The version where the photons arrive one at a time, with measurable gaps between them. That is the version that forced physicists to confront what light really is. And the first person to do that version was a young English physicist named Geoffrey Taylor. Taylor was, in 1909, a graduate student at Cambridge, working under J.J. Thomson. He was interested in whether the wave behaviour of light would persist when the light was made so dim that, on Einstein's photon picture, only one photon at a time could be in the apparatus. He set up a small box, kept in absolute darkness, with a tiny gas flame as a light source. He filtered the light through smoked glass, attenuating it down to extraordinary faintness. Then he sent the dim light through a setup that would cast a diffraction pattern around a fine needle, recording the pattern on a photographic plate. The trick was the exposure time. The light was so faint that Taylor had to leave the photographic plate exposed for months. He calculated that for most of the exposure there was less than one photon in the box at any given moment. If the wave picture was wrong, the diffraction pattern should disappear. There would be no fringes. After 3 months of exposure, Taylor developed his plates. The diffraction pattern was there. The single photons, arriving one at a time, had nevertheless built up a pattern that only a wave can produce. Geoffrey Taylor had shown that a photon interferes with itself. This is one of the strangest sentences in physics. Let me say it again, more slowly. A single photon, travelling alone through an apparatus with no other photons present, somehow behaves like a wave that is large enough to encounter the entire diffraction geometry, large enough to interact with both edges of the needle, large enough to do everything a classical wave does, and yet, when it arrives at the photographic plate, it deposits its energy at a single point like a particle. Taylor's experiment used a needle, but the principle is the same. Modern versions of the experiment using genuine double slits and single photon detector arrays have been done many times. The Harvard Physics demonstration program has a setup that has been shown to students for decades. There are video recordings of single photon double slit experiments, taken with single photon avalanche diode arrays, that show the same thing happening in real time. You can watch the photons arrive, one at a time, as individual dots scattered across a detector grid that initially looks like random noise. And then, as the experiment continues for minutes or hours, the dots accumulate and the random scatter begins to organize itself, and the interference fringe pattern slowly emerges, stripe by stripe, until it is unmistakable. The fringe is there in the final image. The fringe is built from individual particle-like dots. Each dot is the location where a single photon delivered its chunk of energy. And the locations of those dots, taken one at a time, are unpredictable. But the pattern they make in aggregate is the pattern of a wave passing through both slits and interfering with itself on the other side. Let me bring you into one of these experiments just for a moment so you can feel it. Imagine you're standing in a darkened laboratory. The room is sealed against light. The only illumination is the soft red glow of a few status indicators on the equipment. In front of you is a long optical table covered in black anodized aluminum, with mounts and posts and lenses arranged in a careful geometry. At one end of the table is the light source, a laser, attenuated by stacked filters to the point where the light coming out of it carries, on average, less than 1 photon every microsecond. The output, by everyday standards, is dark. You cannot see it. There is nothing to see in the normal sense. But the photons are arriving one by one in pulses too rare for any normal detector to notice. A short distance from the laser, there's a small barrier with 2 narrow vertical slits cut into it, perhaps 200 micrometers apart. Behind the slits, at a longer distance, sits a square array of single photon detectors, each one no bigger than a few micrometers across. The array is connected to a computer that can record the precise pixel coordinate of every detection event. The computer's screen shows, at the moment, a black grid with no marks on it. The experiment is about to begin. Someone presses a button, the detector's arm. The clock starts. For the first few seconds, nothing visible happens. Then, at some point during the first minute, a single pixel lights up on the screen. A small white dot appears on the black grid, at some apparently random location. It is the first photon, 1 pixel out of millions. The pixel has registered a click and the computer has marked the location with a dot. That dot represents a single chunk of energy delivered by a single photon to a single detector. The rest of the wave, whatever the wave was, did not deliver anything anywhere else. The other detectors saw nothing. A few seconds later, another dot appears, then another, then another. The dots arrive at a rate of perhaps 1 or 2 per second. They are scattered across the grid. There is no pattern. It looks like noise. It looks like nothing. But you keep watching. You let it run. Minutes pass, then more minutes. After about 10 minutes, there are perhaps 1,000 dots on the screen. They are still scattered, but if you look carefully, you can see that some areas of the grid have more dots than others. There seems to be a kind of texture forming. After an hour, there are maybe 50,000 dots, and now the texture is unmistakable. There are vertical stripes of high dot density alternating with stripes of low dot density. The stripes are the interference fringes. Bright stripes are where the wave constructively interfered. Dark stripes are where the wave destructively interfered. The fringe pattern has emerged from what looked, an hour ago, like random scatter. And here is what is impossible to wrap your head around. At no point during the experiment was there ever more than 1 photon in the apparatus. Every photon travelled alone. Every photon arrived at the detector individually. And yet the pattern they made together is a pattern that only a wave passing through both slits can make. Each photon travelling alone somehow passed through both slits. Each photon travelling alone somehow interfered with itself. Each photon travelling alone knew, at the moment it landed, which pixels were the bright stripe pixels and which were the dark stripe pixels, and it landed in a bright stripe pixel with high probability, and in a dark stripe pixel with low probability. How did the photon do this? How did it know? The honest answer is that we do not fully know. We have a mathematical description which is quantum mechanics, and the mathematical description tells us exactly what the probability distribution of the dots will be. The math is so good that it predicts the locations of the bright and dark stripes to a precision limited only by how well we can measure the slit spacing. But the math does not tell us what is physically happening between the moment the photon leaves the laser and the moment it lands on the detector. When physicists try to give a picture of what is happening, they fall into a sort of reluctant compromise. They say things like, the photon is, in some sense, a wave during its travel from the source to the detector. The wave really does pass through both slits. The wave really does interfere with itself behind the slits. The interference pattern in the wave's intensity really does have bright and dark stripes. And then, at the moment of detection, the wave somehow collapses to a single point, with the probability of collapsing at any given point being equal to the wave's intensity at that point. This is the standard description. And it is, when you really sit with it, a sentence that does not quite make sense. What does it mean for a wave to collapse to a point? What physical process causes the collapse? Why is the collapse random? What determines which point gets chosen? What happens to the rest of the wave at the moment of collapse? These are the questions that have kept the deepest physicists in the world awake at night for almost a century. They are not answered. There are interpretations of quantum mechanics that try to answer them in various ways, and we will get to some of those in a little while. But none of them is universally accepted. None of them is experimentally proven. They are all stories we tell ourselves to make sense of the math. What the math does commit to is this. Before the detection, the photon is described by a wave function that is spread out across both slits and across the entire region behind them. The wave function has a definite value at every point in that region, and the squared magnitude of the wave function at any point tells you the probability of finding the photon at that point if you measure. The wave function is the photon, in the only sense in which the photon has any properties at all before measurement. It really is spread out across both slits. It really does interfere with itself. It really is, in some sense, that defies the friendly picture, large. And when the measurement happens, when a detector pixel absorbs the energy and clicks, the wave function collapses. The photon, which a moment before was spread across both slits, is now located at one pixel. The energy that was distributed across the wave is, in that instant, concentrated at the absorbing atom in the pixel. The rest of the wave, the parts that did not land on the pixel that clicked, ceases to be relevant. This is the description physics gives us. A photon before measurement is wave-like, spread out, interfering with itself, large. A photon, at the moment of measurement, is particle-like, concentrated, located, small. The wave-like and the particle-like behavior are both real, both essential, both required by experiment, and they coexist in a way that no picture from everyday life can really represent. This is what wave-particle duality actually means. It does not mean that the photon is sometimes a particle and sometimes a wave, the way an object on Earth is sometimes wet and sometimes dry. It means that the photon, all the time, is something that has both wave-like properties and particle-like properties, and that the experimental setup determines which properties show up in any given measurement. The photon is wave-like. The photon is particle-like. The photon is the thing that has both of these properties at once, and the friendly picture cannot accommodate either of them honestly. Where does this leave the question we asked at the beginning? How big is a photon? What is the spatial extent of one of these things? The answer, as we are about to see, is much stranger than even what we have already encountered. The wave-like side of the photon, when described honestly in the mathematics of quantum mechanics, has a spatial extent that is, in the cleanest theoretical case, infinite. A single photon, in its pure form, is the size of the universe. Let me show you why. Part 5. How big is 1? Here is a question that is probably starting to itch in the back of your mind. We have established that a photon is wave-like in some respects and particle-like in others. A single photon travelling alone can pass through both slits in a double-slit experiment and interfere with itself. The same photon, at the moment of detection, lands as a single click at a single pixel. But what does a photon just on its own look like? Before any measurement happens, in the time between leaving the source and arriving at wherever it is going. What is the shape of one of these things? The question turns out to have a surprisingly clean answer in the simplest theoretical case, and the clean answer is something almost nobody outside of professional physics ever encounters. It is, I think, one of the most beautiful and disorienting facts in the entire subject. In quantum mechanics, the state of a single photon, what physicists call a single photon Fock state of a specific frequency, corresponds to a single excitation of one mode of the electromagnetic field. The mode is what physicists call a plane wave. A plane wave has a single sharp frequency. It has a single sharp wavelength. It extends mathematically throughout all of space. It has the same amplitude everywhere. It oscillates in time, and it travels in a specific direction at the speed of light. It has no beginning. It has no end. A plane wave fills the universe with uniform oscillation. When we say a single photon is a single excitation of a plane wave mode, we mean it literally. The photon, in this purest theoretical case, is not a small concentrated thing. It is a single quantum unit of energy distributed across the entire universe. The energy is everywhere. The wave is everywhere. The photon in this description is, in the most precise mathematical sense, the size of the universe. Stop and feel that for a moment. A single photon, as quantum mechanics formally describes it, is not a small bullet of light. It is not a curly squiggle moving through space. It is not a tiny ball. It is a wave that fills all of space. It has the same amplitude in your living room as it does on the surface of Mars as it does at the centre of the Andromeda Galaxy. It oscillates at a single, perfectly defined frequency, and there is one quantum's worth of energy associated with the entire wave, which is to say, with the entire universe. This is not a metaphor. This is not a loose way of speaking. This is what the mathematics of quantum field theory actually says when you ask it to describe a single frequency photon. Because if a single photon is the size of the universe, then what was happening to it during the moment between leaving the lamp in your living room and arriving at your eye? It did not, in any literal sense, travel across the room. There was nothing to travel. The wave was already everywhere. The wave had been everywhere all along. The photon, before you saw it, was distributed across all of space, with a small amplitude in your living room and the same small amplitude in every other place. The act of seeing it was the act of localizing that universe-spanning wave to a single absorbing molecule in your retina. This is an extreme picture. It does not really correspond to most actual physical situations. In most actual physical situations, what we call a single photon is not a pure single-frequency Fock state, but something more complicated. It is what physicists call a wave packet, a superposition of many different frequencies, peaked around some central frequency, with a finite spatial extent set by the spread of frequencies in the packet. We will get to wave packets in the next part, but here is the thing. The wave packet is a compromise. It is a way of making the mathematics of plane waves correspond to something that has a definite spatial location. And the compromise comes at a cost. Specifically, when you build a wave packet that is localized in space, you are no longer dealing with a photon that has a single, sharp frequency. You are dealing with a photon that has a spread of frequencies. The narrower you make the wave packet in space, the broader you have to make the spread of frequencies that goes into it. This is a consequence of Fourier analysis, and it is the same mathematical fact that underlies the Heisenberg uncertainty principle. If you want a photon that is localized in space, you give up some of its definition in frequency, which is to say, in color. If you want a photon that has a perfectly sharp color, you give up some of its definition in space. You cannot have both. The cleanest theoretical photon, a perfect single-frequency Fock state, has zero spread in color and infinite spread in space. It is the size of the universe. The cleanest possible particle-like photon, a maximally localized wave packet, has finite spread in space and an unavoidable spread in color. The friendly picture, the small bullet of light with a definite color, does not actually exist anywhere in the quantum description. It is a fiction. Useful for many purposes, but a fiction. Real photons are either spread across all of space at a single color, or localized in space at a spread of colors, never both. I want to dwell on this because I think it is one of the most quietly unsettling facts about how the universe is built. We are used to thinking that things have definite sizes. A baseball is a baseball, an atom is an atom. We can measure them with any precision we want. Their size is a real property they have. The photon does not have a size in this sense. The photon has a size that depends on how you have prepared it. You can make a small photon by combining many frequencies. You can make a sharp color photon by spreading the wave across the universe. You cannot make a small photon with a sharp color. This is not a limitation of our measurement technology. This is built into the structure of quantum mechanics. The field allows for excitations that look like plane waves and excitations that look like wave packets and superpositions of those. But it does not allow for excitations that are simultaneously sharply localized and sharply colored. Now you might ask, so what is the photon in real laboratory experiments? When somebody says they sent a single photon through a double slit, what did they actually send? In real experiments, single photons are wave packets. They are produced by sources that emit a finite pulse of electromagnetic energy with a known central frequency and a known time width. The most common sources are atoms or molecules in excited states that emit a single photon when they decay, or specially designed nonlinear optical processors that produce pairs of correlated photons one at a time, or attenuated lasers that emit short pulses with so few photons per pulse on average that most pulses contain either 0 photons or 1 photon. Each of these sources produces a wave packet with a finite spread in time and a finite spread in frequency. The spread in time corresponds to the duration of the pulse. The spread in frequency is set by the spread in time through the Fourier relation. A 1 nanosecond pulse has a frequency spread of about a gigahertz. A 1 picosecond pulse has a spread of about a terahertz. The shorter you make the pulse, the broader its color spread. A femtosecond pulse of red light is not red. It contains visible light across a wide range of wavelengths, all combined coherently to make a brief burst of energy. The brevity is bought at the cost of colour definition. Conversely, if you want light of an extremely narrow colour, you have to let the wave persist for a long time. A laser with a 1 Hz spectral line width has to maintain phase coherence for at least a second. During that second, the wave fills a region of space at least 300,000 kilometers long. That is roughly the distance from the Earth to the Moon. The light from a very narrow line laser, if you treat each photon as a wave packet, is the size of the Earth-Moon system. So how big is a photon? It depends. A femtosecond laser pulse photon is a few hundred nanometers long. A nanosecond atomic emission photon is about 30 centimeters long, comparable to the length of a small dog. A photon from a 1 Hz line width laser is on the order of 300,000 kilometers long. A photon from a single frequency Fock state, the cleanest theoretical case, has no finite length at all. The friendly picture, the bullet of light, has no fixed correspondence to any of these. There is no canonical size of a photon. There is only a size that depends on the experimental preparation. I want you to feel the weight of this. Because this is one of the points where physics makes a quiet but absolute departure from common sense. And once you really see it, you cannot quite go back to the friendly picture. A photon is not a thing with a definite size. A photon is a wave function whose size you choose by how you prepare it. So when we said, in part 4, that a single photon passed through both slits in a double-slit experiment, this is now a less mysterious statement. Of course, the photon passed through both slits. The photon was a wave that was at least as wide as the spacing between the slits. The wave passed through both. There was never a single localized point that had to choose one slit or the other. What remains mysterious is the collapse. The fact that the wave can be the size of the room, and then at one instant become the size of an absorbing atom. The fact that the wave's energy, distributed across all that volume, can be delivered to one atom in one instant, with no energy delivered anywhere else. The photon is, in the cleanest theoretical case, the size of the universe. The photon, when measured, is the size of a single atom. These are not two different photons. They are the same photon, in different modes of description, before and after a measurement happens. The transition from one to the other, the moment when the universe-sized wave becomes the atom-sized click, is the central mystery of how light interacts with matter. In the next part, I want to look at the practical compromise, the wave packet, and walk you through why physicists in their everyday work use a picture of photons as wave packets, even though the strict definition of a photon is a plane wave Fock state. But before we go on, just hold on to this picture for one more moment. A single photon, in its purest theoretical form, fills all of space. The universe is filled with photons, each one of them the size of the universe itself, all of them coexisting, all of them oscillating at their own frequencies, all of them ready to deliver a chunk of energy somewhere if the right interaction happens. The night sky you are looking at, the stars, the moon, the dim glow of the Milky Way, is, in this picture, an enormous tapestry of overlapping universe-sized waves, each one carrying a single quantum of energy, each one waiting to land somewhere it can be absorbed. You're made of atoms that are constantly absorbing some of those waves and emitting others. Every cell in your body is a small participant in the great electromagnetic conversation between matter and the universe-filling sea of light. You're not in this sea, you are part of it. This is the real picture of a photon. The bullet was a children's drawing. The real thing is, in every honest theoretical description, immense. Part 6. The working photon. Physicists do not, in their daily work, treat photons as universe-spanning plane waves. They treat them as wave packets. The wave packet is the practical compromise between the cleanest theoretical description of a photon and the messy reality of an actual experiment. It is the photon you can hold in your hand, so to speak. The photon with a definite spatial location, a definite arrival time, and a frequency that is sharp enough for most purposes but not infinitely sharp. The wave packet is what experimentalists send through their slits and detect with their pixel arrays. It is what travels down a fiber optic cable. Let me describe what a wave packet actually is. Imagine that you take a plane wave at one single sharp frequency, and you call it your starting point. It is the universe-spanning oscillation we described in the last part. The amplitude is the same everywhere. The phase advances smoothly with position. It is monochromatic and infinite. Now imagine that you add to it a second plane wave at a slightly different frequency. The two waves are very similar, but their phases drift apart very slowly as you move through space. In some regions, the two waves are in phase with each other, and their amplitudes add constructively. In other regions, they are slightly out of phase, and their amplitudes partially cancel. If you add many such plane waves together, all with slightly different frequencies, all peaked around some central frequency, the constructive and destructive interference between them produces a beautiful result. In one region of space, all the plane waves happen to be in phase with each other, and they add up to a large amplitude. Outside that region, they fall out of phase and cancel each other out, leaving the amplitude small or zero. The result is a localized pulse, a region of large amplitude surrounded by regions of near zero amplitude, that travels through space at the average velocity of the component waves. This is a wave packet. The wave packet has a definite size, set by how many different frequencies you combined and how wide the range of frequencies was. A narrow range of frequencies gives you a wide wave packet. A wide range of frequencies gives you a narrow wave packet. The width of the wave packet in space, multiplied by the width of the range of frequencies that went into it, is a constant of order 1. This is the Fourier uncertainty relation. A wave packet is, in quantum terms, a single photon whose wave function is a superposition of many frequency modes. The most common shape for a laboratory wave packet is what is called a Gaussian wave packet. The amplitude of the wave, plotted along the direction of travel, looks like a bell curve with an oscillation underneath it. The bell curve gives the envelope. Inside the bell, the wave oscillates at its central frequency. The width of the bell is the spatial extent of the photon. The width of the frequency distribution, by the Fourier relation, is the corresponding spread in color. For the kinds of photons used in everyday optics, laser pulses, atomic emission lines, the light from an LED, the wave packets are typically tens of centimeters to a few meters long. A photon from a green helium neon laser is roughly 30 centimeters long. A photon from a single-mode telecommunications laser at 1550 nanometers, used for fiber optic data transmission, is around a few meters long. A photon from an ordinary incandescent bulb with a much broader spread of frequencies is much shorter, perhaps a few micrometers long. I want to walk you through this trade-off because it is one of the most beautiful and counterintuitive features of how light works. Imagine for a moment that you have a single laboratory photon in front of you, prepared as a Gaussian wave packet. You can ask, of this photon, 2 questions. What color is it? Where is it? If you ask the photon what color it is, you measure its frequency. If the photon has been prepared as a wave packet with a narrow spread of frequencies, a long packet, your measurement will return a sharp answer. The photon has a well-defined color, say, green at 530 nanometers, within some tiny uncertainty. The cost is that you cannot say very precisely where the photon is. The packet is long. It could be anywhere within the long extent of its envelope. If you ask the photon where it is, you measure its position. If the photon has been prepared as a wave packet with a small spatial extent, a short packet, your measurement will return a sharp answer. The photon is here within some tiny uncertainty. The cost is that you cannot say very precisely what color it is. The packet was built from many different frequencies, and any of them could have been the one you would have measured if you had asked the color question instead. You cannot fundamentally ask both questions to arbitrary precision on the same photon. This is the position-color uncertainty principle. Let me make this even more vivid with a thought experiment. Imagine you're watching a single photon as it travels across the room from a source to a detector. At some point along its journey, you decide to measure its position. You have a very fine apparatus that can pinpoint the photon's location to within a small region of space. You make the measurement. The photon is located, let us say, in a region 1 centimeter wide. What happens to the photon's color? Before the measurement, you might have thought of it as a single sharp color. After the measurement, the photon is no longer a single sharp color. Its wave function has been collapsed to a position eigenstate within 1 centimeter, and the Fourier transform of that position eigenstate is a spread of frequencies. The photon, by being asked where it was, has become a smear of colors. You can verify this. After the position measurement, send the photon through a prism. The prism splits light according to color. If the photon were still a single sharp color, you would see a single sharp spot on the detector at the far side of the prism. Instead, you see a spread. The photon has been smeared in colour by the act of localizing it in space. This is not a hypothetical. Experiments along these lines have been done with quantum dots and with nanoscale optical confinement, and they show exactly this effect. A photon trapped in a small region of space has a measurably broader spectrum than the source it came from. Now flip the experiment. Imagine you have a photon that you have just measured to be a very specific colour. The wave function is now in a frequency eigenstate. Where is the photon? It is everywhere along the direction of travel, smeared out across a long region of space. I want to dwell on what this means for the friendly picture, the bullet of light. The friendly picture has a photon that has both a definite colour and a definite location simultaneously at every moment. Such a photon does not exist. It cannot be built. The universe does not permit it. Every actual photon is somewhere on the spectrum between sharp colour fuzzy location and sharp location fuzzy colour, and the product of the two uncertainties is bounded below by a constant. A photon, in this sense, is not a thing that has both a colour and a location. A photon is a wave function whose colour distribution and location distribution are Fourier conjugate to each other. The wave packet is a particular choice of how to balance the two distributions, and the balance is, in a real sense, the only thing the photon has. For most everyday purposes, this trade-off does not matter. The photons that arrive at your eye from a screen across the room are wave packets of typical optical sources, short enough to be functionally localized to a region much smaller than the room, with colour spread small enough that you cannot perceive the smearing. The photon, for practical purposes, has a colour and a location. The friendly picture is approximately right. The trade-off is just hidden in the small print. But when physicists do experiments at the limits, single photon interferometry, ultra-narrow line spectroscopy, attosecond pulse generation, nanoscale optical confinement, the trade-off comes out into the open. The photons in these experiments do not look like bullets, they look like packets, and the packets stretch and contract and smear depending on how the experimentalist has prepared them. The photon is the working compromise, the plane wave is the textbook ideal, the bullet is the children's cartoon. None of them is the whole truth. The truth is that the photon is a flexible object whose properties depend on how it has been prepared, and the trade-offs between those properties are built into the fabric of the universe. I have given you the first half of the journey. The photon is granular in energy. The photon is wave-like in propagation. The photon can be the size of a region you choose, with a colour spread determined by Fourier reciprocity. The photon, when measured, collapses to a single click at one detector. The photon, between measurements, is a wave function whose spatial extent and frequency profile are inseparable. This is already a lot of strangeness. But we have not yet asked the question that, for me, is the strangest of all. We have not asked whether the photon has any mass. You might think the answer is obvious. The photon is massless. Every textbook says so. The whole structure of relativity is built on the assumption that the photon travels at the speed of light. But here is the catch. We have never proven in any experiment that the photon's mass is exactly zero. We have only shown that if it has any mass at all, the mass must be smaller than a series of progressively shrinking upper limits. The masslessness of the photon is an assumption. The data is consistent with that assumption, but the data is also consistent with a tiny, almost imperceptible mass. What I want to do next is walk you carefully through what we actually know about the photon's mass, what we assume, and what would change about the universe if the photon turned out to have a tiny mass after all. Because this is the question that, more than any other, reveals just how much of modern physics rests on a foundation we have measured very carefully, but never fully verified. The speed of light is not the speed of light. Not necessarily. Let me show you what I mean. Part 7. The mass question. Let me ask you a question that sounds, on the surface, like one of those silly questions a clever child might ask. Does a photon have mass? The textbook answer is no. The photon, every physics textbook tells you, is massless. It travels at the speed of light because that is what massless particles do. It carries energy and momentum, but it has no rest mass. The reason it can travel at the speed of light is precisely because it is massless. The whole structure of relativity is built around the idea that the photon is the canonical massless particle. This is the textbook answer, and the textbook answer is, on a strict reading, an assumption that has never been proven. Let me unpack what I mean by that, because it matters. Einstein's special theory of relativity has, at its core, a single postulate about an invariant speed. The postulate says that there is a maximum speed at which causal influence can propagate through the universe, and that this maximum speed is the same in every inertial reference frame. Einstein called this speed c. He associated it with the speed of light because, at the time he was writing in 1905, the best available understanding of light was that it was a wave in the electromagnetic field, that this wave travelled at a fixed speed determined by the constants of electromagnetism, and that this speed was, as far as anyone could tell, the maximum speed in nature. But notice what is actually being assumed. The maximum speed of causality is one thing. The speed of light is another thing. The postulate of relativity is about the first one. The identification of c with the speed of light is a separate empirical claim, which depends on the assumption that the photon is massless. What if the photon has a small but non-zero mass? If the photon has a small mass, then the photon travels slightly slower than the speed of causality. The speed of light is no longer the universal speed limit. The universal speed limit is some abstract maximum that no real particle ever quite attains. The photon, like every other massive particle, can be slowed down. Its speed depends on its energy. High-energy photons travel faster than low-energy photons, with all of them approaching but never quite reaching the universal maximum. The speed of light, in this case, is not the speed of light. This is the central paradox we're going to keep returning to, so let me say it once more. The speed of light is not the speed of light. The c in Einstein's equations is the maximum speed of causality in the universe. The actual speed of actual light is whatever it is. If the photon has no mass, the two are the same. If the photon has any mass at all, however small, the two are different. We have never proven they are the same. We have only proven that the difference, if any, is smaller than what our instruments can detect. Why does this matter? Why should anyone care, given that the difference, if it exists at all, is so tiny that no experiment has yet measured it? It matters because the assumption ripples through almost everything we calculate in physics. The structure of Maxwell's equations, the existence of long-range electromagnetic forces, the fact that the universe has a definite cosmic horizon at the age of the universe, times the speed of light, the way we measure distances to distant galaxies, the gauge symmetry of electromagnetism, the fact that the photon has only two polarization states rather than three, all of these depend on the photon being massless. If the photon turns out to have a tiny mass, the corrections are small, but they are not zero. So we have spent a century trying to measure the photon's mass, and a century failing. Every experiment we do says the mass is smaller than what we can detect. The upper limit keeps shrinking as instruments improve, but the answer remains, not zero, just very small. The energy-momentum relation is where the relationship between mass and speed becomes precise. The square of the total energy equals the square of the rest energy, plus the square of the momentum energy. If the mass is zero, the particle moves at the speed of light, always, regardless of its energy. If the mass is not zero, the particle moves close to c at high energies, but never quite reaches it. The speed approaches c asymptotically. For a photon with a very tiny mass, this asymptotic behavior would happen at energies far above what we typically encounter in lab. A photon with a mass at the current upper limit would have a speed essentially indistinguishable from c at any energy you could measure. No instrument can detect a difference that small, but the difference is there if the mass is there, and it has consequences. The first consequence is that different colours of light would travel at different speeds. Higher frequency light, which has more energy per photon, would travel faster than lower frequency light. The faster speed would still be less than c, but it would be closer to c than the slower speed. If you started a pulse of multicolour light from a distant source, the high frequency end of the pulse would arrive first, and the low frequency end would arrive last. The delay between them would depend on the photon mass and on the distance travelled. This is in fact the basis of one of the most stringent experimental upper limits on the photon mass. Astronomers monitor sources of light from distant galaxies that emit brief, sharp pulses across a wide range of frequencies. Pulses, fast radio bursts, gamma-ray bursts. If the photon had a measurable mass, the high-frequency photons in those pulses would arrive earlier than the low-frequency photons, by an amount that increases with distance. By measuring the arrival times of different frequency components and finding no evidence of frequency-dependent delay above what can be accounted for by other physical effects, astronomers set ever tighter upper limits on the photon mass. The 2024 study using ultra-wideband data from the Parkes Pulsar Timing Array by Wei and Wu set an upper limit of approximately 9.5 times 10 to the minus 46 kilograms, equivalent to about 5 times 10 to the minus 10 electron volts per c squared. A separate 2024 study by Wang and collaborators, using a neural network analysis of 32 localized fast radio bursts, set an even tighter upper limit of approximately 2 times 10 to the minus 15 electron volts per c squared. Both of these are upper limits. Neither of them is a positive detection. The second consequence of a non-zero photon mass would be that the electromagnetic force would have a finite range determined by the inverse of the photon mass. The electrostatic potential of a point charge, instead of falling off as 1 over the distance, would acquire an exponential suppression factor at long distances. Similar constraints come from measurements of magnetic fields in the solar wind and in the magnetospheres of planets. If the photon had a finite mass, large-scale magnetic field structures would not extend as far as they do. The 2016 cluster spacecraft solar wind study by Retineau and colleagues set an upper limit of around 1.3 times 10 to the minus 54 kilograms. The third consequence of a non-zero photon mass would be a third polarization state for the photon. A massive photon, according to the Proctor theory, would have a longitudinal polarization along the direction of propagation. We have never observed such a state, so what do we actually know about the photon's mass? We know that, if it has any mass, it is smaller than about 10 to the minus 18 electron volts per c squared from terrestrial measurements, and smaller than about 2 times 10 to the minus 15 electron volts per c squared from fast radio burst dispersion measurements. The upper limits keep shrinking. None of them is zero. None of them has ever been zero. You might say this is a distinction without a difference. If the photon's mass is smaller than what any conceivable instrument can measure, who cares whether it is exactly zero or merely extraordinarily tiny? The universe behaves, for all practical purposes, as if the photon were massless. Maxwell's equations work, special relativity works, cosmology works. What does it matter if there is a tiny correction term lurking at a level below detection? Here is what I would say to that. It matters because the philosophical structure of our theories is different in the two cases. In a universe where the photon is exactly massless, the speed of light is the speed of causality, the gauge symmetry of electromagnetism is exact, and everything fits together with a kind of mathematical elegance that physicists find compelling. In a universe where the photon has a tiny mass, the speed of light is not the speed of causality, the gauge symmetry is approximate rather than exact, and the structure of the theory has an extra parameter that we have to fit by experiment rather than derive from first principles. The two universes are operationally indistinguishable at the level of any experiment we have done. They are very different at the level of what kind of theory we use to describe nature. And here is where I want to be honest with you. We do not know which universe we live in. The data is consistent with both. Our best theories are built around the assumption that we live in the first universe, the one where the photon is exactly massless, because that theory is simpler and more elegant. But the assumption has not been proven. The speed of light is not the speed of light. It might be. It probably is. The simplest and most beautiful theories of the universe say it is, but we have not measured it. The c in Einstein's equations is the speed of causality, a structural feature of space-time that no particle has ever been observed to exceed. The actual speed of actual light is whatever it is. If the photon is massless, the two are the same. If the photon has any mass at all, they are not. For 120 years, physicists have been using the same letter for both quantities, on the assumption that they are the same. The upper limit on the photon mass keeps falling. It will probably continue to fall. It may never reach zero, because no experiment can ever positively confirm an exact zero, only place an ever tighter upper bound. The closest companion question is the same one for the graviton, the hypothetical particle that mediates the gravitational force. The graviton is also presumed to be massless. We have never detected a single graviton, but we have detected gravitational waves, and we have used those waves to set an upper limit on the graviton mass of about 10 to the minus 22 electron volts per c squared. Two of the most fundamental particles in physics may both have tiny masses. They may not. We do not know. In August of 2017, a remarkable event was observed by the LIGO and Virgo detectors. A pair of neutron stars merged about 130 million light-years away, producing both a gravitational wave signal and a burst of gamma rays. The two arrived within about 1.7 seconds of each other, after a journey of 130 million years. The agreement constrains the difference in propagation speeds between photons and gravitons to less than about 1 part in 10 to the 15th. The two are, within that precision, indistinguishable. Both move at the speed of causality, or both move at speeds so close to the speed of causality that no measurement can yet tell which one. The speed of light is the speed of light if the photon is massless. The speed of light is not the speed of light if it isn't. We have built our universe on the first sentence. We have only ever proved the second was almost certainly true. That is the foundation of physics, and the foundation is, ever so slightly, uncertain. Part 8. The shrinking number. There is a number in physics that has been getting smaller for 100 years, and it has not yet reached zero. It is the upper limit on the photon's mass. Every experiment that tries to measure it returns the same answer: smaller than this. Every improvement in technology pushes the number a little lower. Every new physical system that physicists can probe provides another constraint, another upper bound, another way of saying smaller than this, and the number keeps shrinking. If you plotted the history of this number on a logarithmic graph, you would see a clean downward staircase. Each step is a generation of experimental work. Each step reaches lower than the one before it. There is no sign that the steps are converging on zero. They are just descending, sometimes by orders of magnitude per step, sometimes by smaller increments. Physicists keep trying. The number keeps shrinking. We may, in some far future, prove that the photon is exactly massless, but we have not yet. We may, in some other far future, find a positive detection of a tiny mass. We have not yet. Tonight, I want to walk you through the methods that have produced these shrinking numbers, because each of them is its own small adventure. The photon mass is a phantom we are trying to corner. Every method we use is a different cage. Every time the photon does not get caught, the cage opening shrinks, and we try again with a smaller cage. The earliest method is the test of Coulomb's law. Coulomb's law says that the electrostatic force between 2-point charges falls off as the inverse square of the distance. For a massless photon, this law is exact. For a massive photon, the law is approximately right at short distances and increasingly wrong at long distances, with the deviation growing exponentially. If you measure the force between charges at different separations and fail to find any deviation, you can place an upper limit on the photon mass. The famous Williams, Fowler and Hill experiment in 1971 gave an upper limit of about 10 to the minus 14 electron volts per c squared. To go smaller, you need to probe the electromagnetic field at much larger distances. Jupiter's magnetosphere stretches well beyond the orbits of its inner moons. If the photon were massive, that magnetic field would not extend that far. The fact that it does places an upper limit on the photon mass of about 10 to the minus 19 electron volts. The basis for limits placed by Davis, Goldhaber and Nieto in the early 1970s using Pioneer 10 data. Better still, consider the magnetic field of the Sun. The 2016 cluster solar wind experiment by Retineau and colleagues looked at the structure of the magnetic field in the solar wind and asked how that structure would change if the photon had a small mass. They set an upper limit of about 1.3 times 10 to the minus 54 kilograms. The two methods, at very different physical scales, give roughly the same constraint. Both methods say the photon mass, if any, is smaller than about 10 to the minus 18 electron volts per c squared. To go smaller, you need intergalactic distances. Many astrophysical objects emit brief pulses of light that span a wide range of frequencies. Pulsars emit pulses of radio waves at frequencies ranging from a few hundred megahertz to several gigahertz. Fast radio bursts span similar frequency ranges. Gamma-ray bursts can span energies from a few kilo-electron volts to several hundred giga-electron volts. If the photon is massless, all the colours travel at the same speed, and the pulse arrives all at once. If the photon has a small mass, different colours travel at slightly different speeds, and the pulse smears out in time. The amount of smearing depends on the photon mass and on the distance travelled. Plasma dispersion gives a much larger frequency-dependent delay, but with a different functional dependence on frequency, so the two effects can be separated by careful fitting. The 2024 Wei and Wu study used pulsar timing data from the Parkes Pulsar Timing Array, observed with ultra-wideband receivers covering 700 MHz to 4 GHz. Their upper limit was about 9.5 times 10 to the minus 46 kilograms. The Wang and colleagues' 2024 study, using a neural network analysis of 32 localized fast radio bursts, set an upper limit of about 2 times 10 to the minus 15 electron volts per C, squared at 1 sigma confidence. That is the current state of the art, about 2 times 10 to the minus 15 electron volts per C squared from extragalactic measurements, about 10 to the minus 18 electron volts per C squared from solar system and terrestrial measurements. Both are upper limits, both keep shrinking, neither has ever been zero. I want to give you a sense of how small these numbers actually are. The mass of an electron is about 9.1 times 10 to the minus 31 kilograms, so if the photon has any mass at all, that mass is at least 10 to the 20th time smaller than the mass of an electron. The mass of a neutrino is upper bounded by experiments to be at most about 0.8 electron volts per C squared, so if the photon has any mass at all, that mass is at least 10 to the 15th time smaller than the mass of a neutrino. The photon is, if it has any mass, the lightest known particle by a factor of 1,000,000 billion, or it is exactly zero. What would change if a positive detection of photon mass were ever made? First, the meaning of C. If the photon has mass, C becomes a fundamental constant of space-time that is no longer the speed of any particular particle, it is just the maximum speed limit. Second, Maxwell's equations would have to be replaced by the Proctor equations, which include an extra mass term. The gauge symmetry of electromagnetism would become approximate rather than exact. The photon would have 3 polarization modes instead of 2. Third, cosmology would shift. The horizon of the observable universe would become photon mass dependent. The reach of magnetic fields across cosmic distances would become finite. Fourth, the photon would no longer be the canonical massless particle. It would be a massive particle whose mass happens to be very small. None of this has happened. The photon, as far as any experiment has yet shown, is massless. The shrinking upper limit on its mass is consistent with a true mass of zero, just as it is consistent with any non-zero mass below the current bound. We have spent a century narrowing the possibility down. We have not yet eliminated it. The fact that the photon's masslessness is an assumption rather than a proven fact is, I think, a deep and quietly beautiful feature of how science works. The upper limit shrinks, decade by decade. Zero remains within the bounds. We have not detected a positive mass. We have not proven a zero mass. The data is consistent with both. This is what physics is like at the deepest level. Not certainty, just upper limits that keep shrinking, and a horizon of possible exact equalities that recedes as fast as we can chase it. The photon, the simplest particle we know, refuses to confirm its own definition. Now, let us turn to what would change about our universe if it ever did turn out to have a measurable mass, because the consequences are surprising, and they show in vivid detail just how much of what we see when we look up at the night sky depends on the photon being what we have, all along, assumed it to be. Part 9. The Other Universe. Let me ask you to do something for me. Picture in your mind a wide field at night. It is summer. The sky is dark, clear, full of stars. The Milky Way arches overhead. The grass beneath you is cool. Across the field, perhaps 50 meters away, a friend is standing holding a small flashlight. The flashlight is white, which is to say, the bulb emits a roughly even spectrum of light across the visible range: red, orange, yellow, green, blue, and violet, all mixed together to produce what your eye reads as white. Your friend points the flashlight at you and clicks it on. In our universe, what happens? The beam of light reaches you almost instantly. At 50 meters, the travel time is about 170 nanoseconds, far below the response time of your eye. You see a single bright dot of white light, exactly where the flashlight is pointing, and the dot persists for as long as your friend holds the switch. The white light is white. Every color that left the flashlight at the same time arrives at your eye at the same time. Now I want you to imagine a slightly different universe. A universe in which everything is the same as ours, except for one thing. The photon has a small but non-zero mass. Not so small that everyday experience is dramatically different. The flashlight still works. The sun still shines, you can still see. But the photon mass is large enough that, at certain distances and certain energies, the consequences become visible. Your friend points the flashlight again. The beam of light leaves the bulb. Each colour of light in the beam now travels at a slightly different speed, because each colour corresponds to a slightly different photon energy. The blue light, with its higher frequency and higher energy, races ahead. The red light, with its lower frequency and lower energy, lags behind. The whole beam stretches out as it travels. You watch the friend's hand. You see the click of the flashlight switch. And then, instead of a single white dot appearing in your visual field at the location of the flashlight, you see something else. You see a thin streak. The streak begins as a faint blue flash at the location of the flashlight, then the streak extends as a green, yellow, orange band, and finally a red trail brings up the rear. The white light, which left the flashlight as one beam, has arrived at your eye as a long rainbow, stretched out in time. The leading edge is the bluest part, the trailing edge is the reddest part. This is not a fantasy. In a universe with a sufficiently massive photon, this is what would happen. The dispersion of light across colours is what we have been measuring with pulsar timing and fast radio burst arrival times to constrain the photon mass. Now look up at the night sky in this same universe. What changes? The stars are still there, they still shine, they still form the patterns of the constellations. But each star, instead of being a single point of white light, is a small streak. The bluer parts of the star's spectrum arrive first, the redder parts arrive last. If the star is varying in brightness, if it is a pulsating variable, or if a supernova is going off, the variation comes in different colours at different times. At very large distances, this becomes dramatic. The light from a distant galaxy, travelling for 1 billion years, has stretched out so much that different colours are completely separated. The galaxy appears as a glowing prism in the sky, with blue at the leading edge and red at the trailing edge, and a faint smear of all the intermediate colours in between. If the galaxy contains a fluctuating source, the fluctuation comes through in pieces, with each colour delivering its own time series, separated by minutes or hours or days from the others. The night sky in this universe is no longer a fixed pattern of pinpoints. It is a slow chromatic show. Light from the universe arrives sorted by colour, with the bluest light always slightly ahead of the redder light, and the time gap growing with distance. Now turn your attention to the most distant light of all, the cosmic microwave background. The CMB has been travelling toward us for about 13.5 billion years. We observe it as a smooth blanket of microwave radiation, with a temperature of about 2.7 Kelvin. In a universe with a massive photon, the long wavelength end of the CMB spectrum would be cut off. The shape would deviate from the Planck blackbody curve. We observe a clean Planck blackbody curve. The match is so good that it places one of the tightest constraints we have on the photon mass. So if you imagine the night sky in a universe with a massive photon, you have to imagine, beyond the stretched chromatic streaks of nearby stars and the time-separated rainbows of distant galaxies, a darker, more attenuated CMB. In a universe with a sufficiently large photon mass, the observable universe itself would be smaller. Light from beyond a certain distance would not yet have arrived. The cosmic microwave background might be invisible, or visible only at the highest frequencies. These are dramatic effects. They are not, in any plausible photon mass scenario consistent with current data, the universe we actually see. We see a clean CMB, a sky full of unstretched starlight, gravitational waves and gamma rays arriving from neutron star mergers within fractions of a second of each other, fast radio bursts whose dispersion is consistent with plasma effects alone. The photon, whatever mass it has, is small enough that none of these dramatic consequences is visible. But the consistency of the data with a massless photon is not the same as proof that the photon is massless. The dramatic effects I have described would happen at photon masses far above the current upper limits. The current upper limits are so tight that the consequences of a photon mass at the upper limit value would not be dramatic at all. They would be visible only in the most precise measurements. A photon at the upper limit mass would be, for all practical purposes, indistinguishable from a massless photon. There is one more consequence worth mentioning. Gravitational lensing, the bending of light by gravity, is in our universe achromatic. Blue light and red light from the same distant source are bent by the same angle. In a universe with a massive photon, this would no longer be the case. Different colours would be deflected by different amounts. Distant galaxies, seen through massive foreground clusters, would appear as faint rainbows. We do not see this. We see achromatic gravitational lensing, another tight constraint on the photon mass. So when we look up at the night sky in our actual universe, we are looking at a sky whose properties are consistent with a particular set of assumptions about light. Light propagates at a single speed, regardless of colour. Light is bent by gravity by a single angle regardless of colour. Light from the most distant objects in the universe reaches us with its full spectrum intact. All of these facts are properties of a universe in which the photon is massless. All of them are consistent with the universe we actually see, but all of them are also consistent with a universe in which the photon has a mass smaller than the current upper limit. We cannot, from looking at the sky alone, distinguish between exactly zero mass and a mass at the upper bound. The two universes look the same, to all the measurements we have done. They might still look the same when we do better measurements next decade and place tighter bounds. The two universes might never be distinguishable. In the next part, I want to turn from the question of mass to the question of measurement, because the deepest mystery of the photon is not its mass. The deepest mystery is what happens when one of them is measured. The wave that fills the universe gives up its energy to a single absorbing atom. The wave collapses, the atom clicks, the detector pixel fires, and nothing in our theories tells us why one pixel rather than another. This is the question that has haunted physics for 100 years. The answer is not yet known. The question, in fact, has not yet been honestly answered by any physical theory. We describe what happens. We do not yet know what happens. The universe picks, pixel by pixel, photon by photon, click by click, and we do not know how. Part 10. The universe picks. There is a moment in every act of vision that, when you look at it carefully, is the most mysterious thing in physics. The moment is small. It happens billions of times per second inside your eyes. It is happening, right now, all over your retina. And it is, in a deep and unresolved sense, a moment that physics has not explained. Let me set up the moment for you, carefully. A photon, a wave that may, in its purest theoretical form, be the size of the entire room you're sitting in, arrives at the back of your eye. The wave passes through the cornea and the lens and the vitreous fluid. The wave reaches the retina. The retina is a sheet of light-sensitive cells, packed densely with about 130 million photoreceptors, rods and cones, sensitive to different wavelengths and intensities. The wave is spread out across many cells. Many photoreceptor cells are illuminated by the wave at once. Now the wave gives up its energy. It interacts with one molecule of a light-sensitive pigment, rhodopsin in a rod, photopsin in a cone, in one single cell. The pigment molecule absorbs the energy of the photon and changes its three-dimensional shape, twisting from one configuration to another in a process that takes about 200 femtoseconds. The shape change triggers a cascade of biochemical signals inside the cell. The cell sends an electrical signal to your brain. You see a single small flash, somewhere in your visual field, of dim light. That is the act of seeing one photon. Hecht, Schleyer and Perrin showed in 1942 that a dark-adapted human eye can detect, with good probability, a flash of light containing as few as 5 to 14 photons absorbed at the retina, and Tinsley and her colleagues in 2016 demonstrated that humans can consciously detect single photons under sufficiently controlled conditions. The human eye is, in fact, a single photon detector. But here is the question I want to dwell on. The wave was spread across many cells. It carried, in classical wave terms, energy distributed across all those cells. When the wave gave up its energy, the energy went to exactly one cell. It went to exactly one molecule in that cell. The other cells received no energy. The wave, which was diffuse and large, became a single localized interaction at a single absorbing site. How did the wave decide where to go? What physical process selected that one cell out of all the cells the wave was passing over? What selected that one molecule, in that one cell, out of all the rhodopsin molecules in the retina? What selected the moment in time when the absorption happened? The honest answer is nothing did. There is no selecting process that physics has identified. The mathematics of quantum mechanics gives a probability distribution over possible outcomes, a probability for each cell, each molecule, each instant, and one of those outcomes is realized and the rest are not. and there is no mechanism in the theory that distinguishes the realized outcome from the not realized outcomes. The wave, the math says, collapses to one location. The math does not say why. This is what I have been calling the universe picking. The picking is the quantum collapse, the moment when a wave function spread across many possibilities suddenly takes a definite value at one possibility. The picking is, in the standard formulation of quantum mechanics, fundamentally random. It is not the kind of randomness that hides deeper determinism, like the randomness of a coin flip that is really just the result of complicated initial conditions we cannot track. It is, as far as anyone has been able to prove, irreducible randomness, built into the structure of the universe. I want you to pause and feel that. The act of seeing, the most ordinary thing in your daily life, depends on a random process that no physical theory currently explains. Every photon that has ever landed on your retina has done so because of a quantum mechanical collapse that selected your retina, that specific cell, that specific molecule, by means that physics describes as random. The universe picked you, and that location, and that moment, and then it picked you again, billions of times per second. Every second you have been alive, in every direction your eyes have been open. The whole experience of vision is built on this picking. Every photograph you have ever taken with a camera is built on this picking. Each pixel of the camera's sensor is the site of a quantum collapse, where a photon could have landed, but most of the time did not. And the image is the cumulative pattern of where the photons did land. Every image of every distant galaxy, every photograph of every loved one, every video you have ever watched, all of these are made of pixels, and each pixel is the site of an enormous number of quantum collapses. The universe picks, it picks again, it picks again. Every act of measurement, every absorption of a photon by an atom, every interaction between light and matter is a moment of selection that the universe makes. And we describe the statistics of the picks with extraordinary precision. Quantum mechanics gives us the probability distribution to any digits we care to calculate, but we cannot from inside the theory identify what the picking is mechanistically. This is the measurement problem in quantum mechanics. It is the deepest open question in the foundations of physics, and the photon is the test case that brings it most clearly into focus. Let me walk you through what some of the major interpretations of quantum mechanics say about the picking, so you have a sense of the menu of philosophical options. The most common interpretation, the one taught in introductory quantum mechanics courses, is the Copenhagen interpretation. The Copenhagen interpretation says that the wave function is a complete description of the system between measurements, but at the moment of measurement, the wave function collapses to a definite outcome, and the collapse is fundamentally random. The probability of each possible outcome is given by the squared magnitude of the wave function at that outcome. The Copenhagen interpretation does not provide a mechanism for the collapse. The picking in Copenhagen is a primitive notion. The universe does it. We describe the statistics. No deeper explanation is offered. The many worlds interpretation, first proposed by Hugh Everett in 1957, says that the wave function never collapses. Every time a measurement happens, the universe splits into multiple branches, with each branch containing one of the possible outcomes. There is no picking in this view. The universe contains all the possible outcomes in parallel, and the experience of seeing a particular outcome is what it feels like to be in one branch of the universe rather than another. The randomness of measurement is not real, in many worlds. It is just the appearance of randomness from inside one of many branches. The GRW interpretation, named after its proposers Girardi, Rimini, and Weber, modifies the Schrödinger equation by adding a stochastic term that causes spontaneous wave function collapses at random times. For single particles, these events are too rare to notice. For macroscopic objects, they are frequent enough that macroscopic superpositions cannot persist. The picking in GRW is real, and is explained by an explicit modification of the dynamics. Pilot wave theory, originally developed by Louis de Broglie and David Bohm, says that there really are particles, in the classical sense, point objects with definite positions at every moment, but they are guided by a wave function that determines their motion. The apparent randomness of measurement is, in pilot wave theory, the result of our ignorance about the initial positions of the particles. Relational quantum mechanics, proposed by Carlo Rovelli, says that the wave function describes the relationship between systems rather than the state of one system in absolute terms. A measurement is an interaction between two systems, and the outcome is real relative to the systems involved. Each interpretation gives a different answer to the question of what the picking is, but no interpretation is universally accepted, and no interpretation has yet been experimentally distinguished from the others in a way that all physicists agree settles the matter. But here is the brutal truth. After a century of work, the question of what physically happens at the moment of quantum measurement is not settled. We have multiple interpretations, each one consistent with the data, each one making slightly different claims about the underlying reality. The community of physicists is divided. Some physicists say it does not matter, that what matters is what we can calculate, and the interpretation is just philosophy. Other physicists say it is the deepest question in their field, and that not knowing the answer means we do not really understand what light is. The picking in our actual universe is something we can predict in distribution but not in detail. We can tell you exactly what fraction of the time a particular detector pixel will fire in a given experiment. We cannot tell you for any individual photon which pixel will fire. We cannot in fact predict the location of any individual single photon detection event, even in principle, given complete knowledge of the wave function. The photon, in the moment of being measured, escapes our description. I want to sit with this for a moment longer, because I think it is the moment in this video where the strangeness of what light really is becomes most personal. You're looking at this screen, or you're listening to my voice. Either way, light is right now entering your eyes. Each photon that arrives at your retina is a wave that has, in the moment just before it absorbed, collapsed to a single absorbing atom in a single photoreceptor cell. The collapse was random, in the sense that no physical process in any theory we have yet developed determines which atom would absorb. The wave was big, the size of the room, the building, the universe in some theoretical limit. The atom is small, a few angstroms across. The transition from one to the other happened in less than a femtosecond, and the universe, every time it happened, picked. You are made of moments of this picking. Your visual experience is a stream of moments of this picking. Every memory you have of light, every photograph in your album, every scene you have ever observed is a tapestry of trillions of these moments, each one a moment when a wave the size of the room collapsed into a click the size of an atom, and the universe selected one specific point out of all the possibilities for the energy to land. We do not know what the selection is. We do not know what physical process determines the outcome. We have built every camera, every fiber optic, every solar panel, every photovoltaic cell, every detector array, and every observatory and every laboratory on Earth on top of this picking. And the picking remains, even after a century of careful physics, something we describe but cannot explain. This is, I think, the deepest emotional anchor of this whole journey. The most ordinary experience of your daily life, the simple act of seeing, is structurally entangled with one of the great unsolved problems in physics. There is no way to look at anything, ever, without participating in the picking. There is no way to read these words, or listen to these words, without thousands of these collapses happening on your retina or in your ears at every moment. The universe picks. You see, it picks again. You see again. Across decades, across a lifetime. And the picking, the universe's quiet selection of one pixel out of many possibilities, is what builds every image, every memory, every sight, every sky. A thing the size of a sky lands on a thing the size of an atom, every time you see. Let me carry this thought into the next part. Because the picking is not the only mystery. The picking is one of many things about the photon that physics describes precisely, but does not understand. Each one, on its own, would be a fascinating puzzle. Together they paint a picture of a particle that escapes every category we have for it. A particle that, after 100 years of study, remains the most carefully measured and least understood object in physics. Let me show you the whole picture. Part 11. The photon nobody can describe. Let me try, here in this part, to gather all the threads we have followed and see if I can describe, in plain language, what the photon actually is. I am going to try, and I am going to fail in a way I want you to feel. Because the failure is the point. The photon is a particle that defeats description. A photon is a wave. It is a wave in the electromagnetic field, an oscillation of electric and magnetic disturbances that propagate together at a speed we have measured with extraordinary precision and have built into our definition of distance itself. The wave has a frequency, which determines its colour in the visible range. The wave has a wavelength, which determines its spatial structure. The wave has an amplitude, which determines its intensity. The wave is, in its purest theoretical form, a plane wave that extends infinitely through space. In its practical form, it is a wave packet localized to some finite region. A photon is a particle. It is the smallest indivisible unit of electromagnetic energy that can be exchanged with matter in any single interaction. The unit has an energy proportional to the wave's frequency, with the constant of proportionality being Planck's constant. When the wave delivers its energy to an atom, the energy goes in a single chunk of this discrete size to one electron in one atom, with no fractional delivery possible. The particle has a momentum equal to its energy divided by the speed of light. The particle can collide with other particles, scatter off them, and exchange momentum with them, as Compton showed in 1923. These two descriptions cannot, in any classical sense, be true at the same time. A wave is spread out. A particle is localized. A wave delivers energy continuously. A particle delivers energy at a point. The friendly picture from childhood, a small bullet of light travelling in a straight line, combines elements of both pictures but represents neither honestly. The wave is not a small bullet. The particle is not a small wave. The photon is something that is, at one moment, the size of the universe, and at the next moment, the size of an absorbing atom. We call this combined nature wave-particle duality, but the name names a paradox, not a resolution. A photon has a speed. Light travels at the speed of light, 299,792,458 meters per second. This speed is invariant in every inertial reference frame, which is the foundational postulate of special relativity. We have measured this speed so many times, in so many ways, that the meter itself has been redefined in terms of it. A photon may have a mass. We have spent a century trying to measure whether the photon has any rest mass at all, and the answer keeps coming back, smaller than this. The upper limit has shrunk by orders of magnitude as instruments have improved. The most recent upper limit from a 2024 neural network analysis of fast radio bursts is about 2 × 10 to the -15th electron volts per c squared. The number is small, it is not zero. We do not know whether it is exactly zero or merely very small. If the photon has any mass, the speed of light is not the speed of light. The speed of light is whatever speed actual photons happen to travel at, which is slightly less than the universal speed limit. We have built our entire science of physics on the assumption that the photon is massless, and that therefore the speed of light is the speed of causality. The assumption may be exact. The assumption may be very nearly but not exactly exact. We do not know which. The speed of light is not the speed of light. We say it is, we calculate as if it is, we build cosmology on the premise that it is. But we have not proven it. The photon, our messenger of causality, may carry a tiny secret that we cannot extract. A photon has a position, in some sense. We can ask where it is, and we can build detectors that answer the question. The detectors return clicks at specific points. The clicks are real, sharp, well-defined events. But the photon, between measurements, does not have a position in the standard quantum mechanical sense. There is no position operator for the photon in standard quantum field theory. The closest mathematical analogue is the Bialynicki-Berula wave function, formulated in 1996, which represents the photon in terms of the Riemann-Zilberstein vector. This wave function propagates through space and time. It collapses upon measurement, but it is not a position-space wave function in the same sense that an electron's wave function is. A photon has no rest frame. In every other particle in the standard model, there is some reference frame in which the particle is at rest. For an electron, you can imagine a frame moving along with the electron, in which the electron has zero velocity. For the photon, no such frame exists. The photon, if it is massless, travels at the same speed in every inertial reference frame, and no frame can ever be co-moving with it. The photon never sits still. Among all the elementary particles, only the photon and the gluons have this property. The gluons, however, are permanently confined inside hadrons and cannot be observed in isolation. The photon is the only particle in physics that travels freely and yet has no rest frame. A photon has a polarization. The wave-like nature of light includes a polarization state, which describes how the electric field of the wave is oriented in space. Light can be linearly polarized, circularly polarized, or in any mixture or superposition of these states. The polarization is a property of the photon that can be measured, manipulated, and used. Polarizing filters in cameras, polarizing sunglasses, the polarization-sensitive detectors in radio telescopes. All of these depend on the polarization of light being a real, measurable property. A photon has only two polarization states if it is massless. The standard model treats the photon as having two transverse polarization modes, perpendicular to the direction of propagation, but no longitudinal mode. This is a consequence of the photon being massless. A massive photon, according to the Proctor theory, would have a third, longitudinal polarization mode. We have not observed such a mode. A photon has no electric charge. The photon is its own antiparticle. Two photons can scatter off each other only through extremely weak quantum corrections. Photons, in this sense, are loners. A photon obeys statistics that are unique to its kind. Photons are bosons, which means many photons can occupy the same quantum state simultaneously. This is why laser light is possible. A photon can also exhibit anti-bunching. Light from a single emitter produces a photon stream in which the photons are anti-correlated. You almost never see two photons close together in time. Anti-bunching was first observed by Kimball, Dagenais and Mandel in 1977, and it is, by itself, a definitive proof that light cannot be purely a classical wave. A photon delivers its energy in a single chunk to a single absorbing atom. The location of the absorption is unpredictable in principle. This is the photon, as physics describes it in 2026. It is a wave that fills space. It is a particle that lands at a point. It has a sharp color that comes at the cost of being spread out in space, or a sharp location that comes at the cost of being spread out in color. It may have no rest mass. It probably has no rest mass. It might have a tiny rest mass we have not yet been able to measure. It has no rest frame. It has no position operator. It has two polarization modes that are observable, and possibly a third that is hidden. It exchanges energy with matter in discrete chunks. It exchanges momentum like a particle. It interferes like a wave. It delivers its energy to one place at one moment, and we cannot say why. This is the most carefully studied particle in the history of physics. We have measured its properties to 12 decimal places of agreement with theoretical predictions in quantities like the anomalous magnetic moment of the electron, which is computed in quantum electrodynamics by summing diagrams in which photons are exchanged between virtual particles. The agreement is the most precise verification of any physical theory in the history of science. By any standard of how well we can predict the photon's behavior, we understand it. And yet, if I ask the simple questions, how big is it? Does it have mass? Why does it land where it lands? The answers come back. It depends. We are not sure. We cannot tell you. Precision and understanding, it turns out, are not the same thing. We can predict the photon's behavior to extraordinary precision. We do not know what the photon is. This is the contradiction I want you to feel. The most precisely understood object in physics is, simultaneously, the least understood. Every photon that has ever entered your eyes has been a particle whose properties physics describes precisely and explains incompletely. Every act of seeing has been a small encounter with something that science has not finished investigating. The speed of light is not the speed of light. I have said this many times now, and I want to say it one more time, but with the full weight of what it has come to mean. The speed of light is not the speed of light, because the photon may have a tiny mass that no instrument can yet detect. We have built our universe on the assumption that the photon is massless. The assumption is, at minimum, exact to within parts in 10 to the 15th. The speed of light is not the speed of light, because the photon is not, in any honest mathematical description, a fixed speed entity moving through space. It is a wave function that propagates according to the laws of quantum field theory. The speed of light is a parameter in those laws, not a property of the photon per se. And finally, the speed of light is not the speed of light, because the word photon itself may not name what we think it names. The photon is a wave. The photon is a particle. The photon is a wave function. The photon is a quantum of excitation of a field. The photon is a click on a detector. All of these are real aspects of what we call a photon. None of them by themselves is a complete description, and the word photon, when we use it in everyday physics, smuggles the assumption that all these aspects are the same thing. They may not be, or they may be, and we have not yet found the framework that shows us how. Either way, the word photon is, in some sense, a placeholder, a name we use because we have no better name. The thing the name points to is the thing physics has studied for a century and described in its math with remarkable precision, and explained in its concepts only partially. You are made of moments of seeing. Every moment of seeing is a small encounter with this incomplete thing. You have spent your whole life in conversation with light that physics has not finished describing. The photon, in the end, is the witness to your every visual experience, and the witness has not been fully introduced. This is the photon. This is what physics knows about it. This is what physics does not know. A thing the size of a sky lands on a thing the size of an atom. Every time. Every time you see. Part 12. The Open Question. We have come a long way tonight. Let me try to bring you gently back to where we began, so you can see how the journey has changed the meaning of the things you already knew. We began with the friendly picture, a small bullet of light, a tiny ball moving in a straight line at a fixed speed, a photon. The picture was simple, intuitive, and comfortable. It is the picture most people carry around in their heads when they hear the word photon. It is the picture in most children's books about science. It is the picture that, on a casual reading, lets you make sense of the basic facts about light without having to think very hard. I told you at the start of this video that we were going to take that picture apart, and that what we would replace it with would be something stranger and more beautiful. Now we are at the end of the journey, and I want to ask you to compare the two pictures. The friendly picture, a small ball, travelling fast, carrying energy, hitting things and giving them light. The real picture, as physics describes it now, a wave that may be the size of a room or the size of the universe, propagating at a speed that may or may not be the universal speed limit, carrying discrete chunks of energy that can only be delivered in indivisible units, determined by the wave's frequency, with no position operator, no rest frame, possibly no mass at all, but also possibly a mass so small no instrument has ever measured it, exchanging energy with matter through a process of random collapse to a single point that no theory has yet been able to explain mechanistically. The same kind of wave and particle entity that all of quantum mechanics is built around, the carrier of every photograph and every memory of light you have ever had. The two pictures cannot be compared as if they were two more or less accurate descriptions of the same thing. They are descriptions of different things. The friendly picture is a cartoon. The real picture is what physics has been trying to write down for 100 years, and is still writing. I want to be careful, here at the end, about what I claim. I have used dramatic language throughout this video. The speed of light is not the speed of light. The photon is the size of the universe. The universe picks. A thing the size of a sky lands on a thing the size of an atom. These are evocative phrases, and they capture something real about the strangeness of light at the quantum level. But I want to be clear that the strangeness is not, in any simple way, an indictment of physics. Physics is doing remarkably well at describing all of this. Our equations work. Our predictions match experiments to dozens of decimal places. Our technology, every laser, every fiber optic line, every solar panel, every camera, every quantum computing apparatus, is built on top of these descriptions, and it all works. What is unresolved is not the practical question of how to compute and use photons. That is solved at a level of precision that is the envy of every other branch of science. What is unresolved is the conceptual question of what we are computing about. What kind of thing is the photon, in the deepest physical sense? What is the mechanism behind the random collapse at measurement? Whether the photon has a tiny mass or no mass at all. What it means for a wave to be spread across an entire room and then deliver its energy to one atom in one instant. These are open questions. Some of them may be settled in the next century, some of them may never be settled. So I want to leave you tonight not with an answer, but with the openness of the question. Maybe in some future decade a physicist will perform a measurement so precise that it positively detects a tiny photon mass. The standard model would have to be modified. The Proctor theory, with its longitudinal polarization mode, would become the new framework for understanding electromagnetism. The c in Einstein's equations would no longer be the speed of light, but the speed of causality, the speed limit that no actual particle ever quite reaches. Light would join the family of massive particles that includes everything else in the universe. Maybe, in some future decade, a physicist will perform a measurement so precise that it pushes the upper limit on the photon mass below all theoretically motivated possibilities, effectively confirming that the photon is, for all intents and purposes, exactly massless. It would confirm that the photon is special, that the electromagnetic gauge symmetry is exact, that the speed of light truly is the speed of causality. Maybe, and this is the most likely outcome frankly, neither will happen, and the upper limit on the photon mass will simply keep shrinking, as it has done for a century, without ever reaching either zero or a positive detection. The photon will remain an open question, asymptotically approaching the assumptions we have made about it, but never definitively confirming them. Maybe, in some future decade, the measurement problem of quantum mechanics will be resolved. Spontaneous collapse experiments will detect a positive signal, or a clean test will be performed that distinguishes many worlds from Copenhagen, or some new theoretical framework will be developed that explains, in physical terms, why the universe picks one pixel over another. Maybe none of these will happen, and the measurement problem will remain unresolved, and a century from now, physicists will still be having the same arguments about what really happens at the moment a photon is detected. I cannot tell you which of these futures we will inhabit. I cannot tell you definitively what the photon is. Nobody can. The physics, even with all the technology and ingenuity of the past 100 years, has not yet given us that answer. What I can tell you is that the photon, whatever it is what your eyes have always been catching. Every sunrise you have ever watched, every face you have ever looked into, every star you've ever stared up at, all of it has been a long collaboration between you and these strange wave particles that the universe is filled with. You have been participating in the great unsolved mystery of physics every time you've opened your eyes. I find this thought, when I sit with it, not anxious, but quietly beautiful. The world is more open than it looks. The simplest things, light, colour, vision, are not yet finished puzzles. Physics has driven itself to extraordinary precision in describing how the universe works, and at the same time it has driven itself to extraordinary humility about the deeper question of what the universe is. The two go together. The more precisely we describe, the more clearly we see the gaps between description and understanding. You and I have come a long way through this video. We started with a friendly picture, a small bullet of light. We turned the picture over and looked at it from many angles. We watched it crack at the photoelectric effect. We watched it crack at single photon interference. We watched it stretch into a wave the size of the universe. We watched it compromise into a wave packet of finite size and finite colour. We watched it submit, possibly, to a tiny mass we have never measured. We watched it collapse at the moment of detection into a single click on a single pixel by a process the universe performs without explaining. The friendly picture, the cartoon ball, is too small for the thing it represents. The real thing is enormous. It is the carrier of every visible signal in the universe, the messenger between every star and every eye, the agent of every interaction between light and matter that has ever happened. And it is, after a century of careful study, still an open question. So when you finish watching this video and you look up, at the screen, at the wall, at the window, at the night sky if you can see it from where you are, I want you to remember the picture we have just walked through together. The photons arriving at your eyes are not small bullets. They are wave functions, vast in extent, oscillating at their frequencies, propagating across whatever distance separates the source from you. They are arriving, billions per second, each one in a state spread across some region of space, each one terminating its existence as a wave at the moment it collapses into a click on one absorbing molecule in one of your retinal cells. The collapse is random, the wave is large, the atom is small, the universe picks, you see. A thing the size of a sky lands on a thing the size of an atom. Every time you see, this is the photon, this is what we have spent a century studying, this is what we still do not fully understand, and this is what is right now entering your eyes from every direction the universe can send light, asking to be witnessed, agreeing to be the thing that lets you see the world, withholding the deepest secret of what it actually is. Maybe one of you, watching this, will be the person who finally figures it out. Maybe in some future laboratory, a clean experiment will deliver the answer that has eluded the field for so long. Maybe a new theory will reframe the question in a way that dissolves the mystery rather than solves it. Maybe the question will outlive all of us, and the photon will remain for centuries to come the simplest particle physics knows about and cannot quite describe. Whichever it is, the photon will go on doing what it has always done. It will go on carrying the light of stars across cosmic distances. It will go on warming the Earth. It will go on entering the eyes of every living creature that has eyes. It will go on collapsing at each act of vision from a wave into a click. It will go on building the world we see, and the world we see will continue to be, in every honest sense, made of mystery. Carried by something physics has measured 1,000 ways and still, after all that, cannot describe. Sleep well. Look up. The photons are waiting. They have, in their quiet way, been waiting all along.